Hello, we're back. Now we're back here looking at the Stockton Bar in Utah again. We have LiDAR data that's over a small area near actually the town of Stockton and the Stockton Bar, which is Lake Bonneville, depositional feature. And then we have in color here this AGRC. It's a mosaicked 2-meter data set. Showed how to mosaic to new raster in a prior video. And then in the background we have this 10-meter national elevation data DEM. So in the end we're going to want to compare kind of how the elevation or how the pixels of these three different scaled data sets, 1 meter, 2 meter, and 10 meter, represent the landscape over the same area. And so what we're going to do first is to clip all the data to the same extent so that we can look at the statistics of each of those data sets over that same area to see how they vary. It's also going to help if you're going to subtract one area from another. Tend to find that in a raster calculator that if they are not over the same extent, that sometimes it leads to a failure in processing. Okay, so what we're going to do is create a clipping mask over the area where their smallest data set is, and we're going to use that to clip all of the other DEMs. I'm going to remove some things that aren't needed anymore and to keep things a little simpler. And then so we're going to want to go back to find a tool. Well, actually, what we can do, I believe, to do this would be to simply make a shapefile of the area, a shapefile or rather a feature class of the area where Stockton Bar's 1 meter LiDAR data exists, the smallest data set. And so there's a number of ways that one could do this. I often I like to basically we can do I think it's called conversion tools from raster to polygon. We might be able to go ahead and try that right now. So let's do that. So that's within conversion tools, raster to polygon. Our input raster could be the LiDAR slope or the DEM underlying it, which is called bar clip. Let's do that, bar clip. It's not happy for some reason. The input raster is not within the defined domain. It is not an integer type. That's what I thought. We need a raster to be basically integer. We need to tell it where it should make the polygon or not. So first we're going to turn it into an integer. We can do that within spatial analyst tools. So spatial analyst tools is down here. And then there's something called reclassify. And you can just go reclassify. So we can input our bar clip, and we can classify values within there. So we have a lot of values in there. So one way to make this a little bit easier, I mean, you can classify, I suppose, all values. So that's what we could do. So we can make one classification. So basically less than the peak value, okay, is equal to 1. And the rest is called no data. And this we're just going to use very temporarily, so I'll just leave it as kind of a temporary file. And yeah, I'll change missing value to no data. So we'll run that. It should just make a raster where every pixel is the size of the input, and it has a value of 1. So it should be looking like one color across the raster. Okay, it has appeared, and boom, we have this solid color showing us where that raster exists. Now we can go back and go back up to conversion tools from raster to polygon. And if we input our reclass raster and the value and create polygon features, so every value will have a separate polygon, which is, I guess, why they wouldn't have accepted it, right? If we just threw in the DEM, because there's so many unique values, it would have been quite annoying. So I'm going to simplify polygons, and this should work. So my output feature, let's save that temporarily in my practice folder, since it might want us to, I think it's going to be okay. So we'll call this bar clip poly. Okay. Run. Okay, my bar clip poly appeared. So you might ask, why couldn't we have just clipped a raster using the reclass raster or the LiDAR slope or bar clip itself? Well, the reason for that is rasters are basically rectangles, and so underlying them, wherever there's kind of a weird geometry, is no data. And so if you used it to clip something else, it's going to make a rectangle at the kind of limits of the kind of X and Y positions instead of the geometry that we want. And so with the feature class or shapefile, we can get a very unique, specific geometry, basically like a cookie cutter, to make things very precise. Okay, so we have our clipping polygon. The next set of things that we need to do is to basically clip these rasters. So I'm going to go to Data Management Tool, and I'm going to go to Raster, I believe, and let's see if we can find clip. Raster processing, clip raster. So it's under Data Management Tools, Raster, Raster processing, clip raster. So we could input one of these larger rasters. We can start with the AGRC DEM 2 meters. And the output extent, yeah, we can say the bar clip polygon. But if we don't choose anything else, again, it's going to give this XY coordinate rectangle. So we need to click this, use input features for clipping geometry. And then we need to give it a name. Let's go back into my practice folder. Yeah, we can call it AGRC. It's really a 2 meter DM because I reprocessed it to that. 2 meter clip. .tiff. That should work. So let that process a minute. Hopefully it's not going to take too long. Building pyramids. Okay, it ended up showing up below my poly polygon. Yeah, there it is. We can see it. So I can now turn this other one off, and it's sitting there on top of this NED. So we now need to do the same thing for the NED. It's NED 10 meter. We want to still use the same clipping extent, and use the input clipping geometry of that bar clip poly shape file. Now we need to give it a new name, and in this case we'll call it NED 10 meter clip .tiff. Okay. Boom. Done. Very fast. Let's see if it's really there. So, yeah, it's sitting there on top. Okay, so I can turn off the background. And so let's, just to prove it to ourselves, let's color each of these differently. So our NED is going to be kind of these psychedelic colors. We'll keep our AGRC as black to white. And we got the LiDAR slope. We have a LiDAR bar clip that we started with. So we know that's there. So let's see. NED, clearly there. AGRC there. There's our reclass. There's our LiDAR slope. We'll turn that off. We should see the LiDAR itself underneath. If we now zoom in, we should get a handle, once the pyramids load, kind of how smooth or not these data sets are. So that's the smoothest one, the LiDAR bar clip. And then if we load the 2 meter data, it should still look pretty smooth, but perhaps a little fuzzier. Let's see if we can distinguish that. Yeah, I think I can see that in there. I also see some change. And then the NED, I can see the pixels on that. Okay, so yeah, there's our data sets. So if you're too sick of that psychedelic color, we can go back to something more typical. Okay, so now we have these 3 data sets, and they're all clipped to the same extent. And so why is that useful for us? Well, I wanted to, in this lab, you know, you're comparing the data sets kind of in a global sense, a global analysis. We can do that. We could have done that using a polygon in what's called a global analysis with within spatial analyst tools. We can go under spatial analyst tools. So I'll show you where that is. And basically do kind of certain types of statistical analyses. So that would be zonal statistics. So we could compute the statistics within the zone of the bar clip polygon, which is effectively what we're going to do as well. But since we've clipped them to the exact same area, we can simply look at the statistical data embedded within these new rasters that we've created. And there's 2 places to look for them. Okay, so you can go into properties, and in the source, within layer properties, we can click on statistics. We can see the minimum elevation. You can see we have a lot of decimals, way more than is realistically accurate. The maximum elevation, the mean elevation, and the standard deviation is shown here for elevation data across the area of the Stockton bar only. And so let's look at that just for a second. So if we go back there, we can just remember in our head the minimum elevation or the maximum elevation or the mean. How about let's do the mean? So the mean is 1665 meters. 1665. Okay. So if we go to the AGRC, we go to properties, source, statistics, the mean is 1666.7. So it's just about a meter higher on average than the NED. And it should be higher because the NED is made from old topographic surveys, which were quite accurate and were focused on the land surface, whereas the AGRC's 2 to 5 meter DEMs that were produced from air photos. And so some of the they're basically digital surface models of the Earth rather than terrain models. And so we see buildings, we see trees, etc. So it should be taller on average. So that makes sense. If we look at the LiDAR, if it is ground classification, it should look more like the NED, but I'm not sure how well that is. We could look for how well that's been done. We could look at the slope quickly. Let's see. So if we zoom in, actually we do see quite a few trees. So I'm going to say the average elevation might be higher than the NED, although that could be offset from what you guys are doing in your lab. One thing is to see change in the landscape. And we do see a lot of gravel mining, which may not have been there when those original topographic surveys was done. So it could be lower too. Let's go see. Properties, statistics. The mean is 165.7. Pretty close. So they're all representing the landscapes quite similarly in terms of average elevation. You may see some differences in the minimums or the maximums. When you do run a slope analysis, though, you're going to see quite big changes because the peak slopes in the LiDAR should get quite steep, nearly vertical, given that it's representing the landscape at 1 meter or half a meter pixel. There are those size cliffs in this landscape. But in this landscape, there are no big tall cliffs. So with a 10-meter DEM, it's definitely going to have lower maximum slopes. Okay, so there's another way to look at this statistical information very quickly within the raster data sets, and that's under symbology. And so when you go into symbology, if you change how you're displaying it to classify, it allows you to kind of investigate the histogram to inform your classification. So we can see that, you know, the peak values up here are 2,245 meters. There's not too many like that, and so the more of the elevation pixels are down here below 1,600 meters. And so that kind of gives you a visual sense of the data, but you can also click Show Statistics, which will give you the minimum, the maximum, the mean, the standard deviation. This should be exactly what's shown under the source data, but more interesting is the number of pixels represented. And so here in the LiDAR we have 66 million plus pixels. If we compare that with the NED, so if we go into the symbology of the NED, sorry, this is huge, and we go to classify again, and click on histogram, and click statistics. Yeah, we'll see that only less than 200,000 pixels instead of 66 million pixels are required to represent the landscape. We see that other statistical data as well. Also within the NED, we can look at the properties. If you look at just the raster information, it'll show you how many columns and rows. Remember, they're rectangles. And also the uncompressed size, 1.42 megabytes for the national elevation data 10 meter. 1.42 megabytes, less than a song on your phone if you're to use an MP3 download. Whereas if you compare the same area within the LiDAR data, raster information, it's half a gigabyte, 473 megabytes. So yeah, it's a lot more costly. So, you know, can always think about what is and isn't necessary for kind of comparing or doing some topographic analysis. So if you're only interested in gross scale things like what's the relief across a landscape, probably a low resolution DEM is going to do a good job. But if you're really interested in the morphology, trying to understand processes in the landscape, then you're going to want some higher resolution LiDAR or maybe even a point cloud. Okay, so one last thing I'll show you, now that we've got them all clipped to the same sizes, we can do some raster math on them. And so the raster math is in Spatial Analyst tools. Actually, don't be careful. I called it raster math. That's there, and we can do that, but prefer to use the calculator. It's a little bit more agile. So we can subtract one DEM from another. Remember that when we're comparing or interrogating a digital elevation model, we don't want to subtract its products. We want to subtract it, so leave the slope alone. But if we've got our clipped files, we can say agrc subtract NED, and I'll just make a temporary file. So this is going to say, let's take that 2007 agrc 2 meter DEM, subtract it from that 2004, I think, but the data comes from older than that, topographic surveys from prior to 2000 most likely. So we're at least 7 years of change, but also different pixel size. And let's see how that goes. So because they were different pixel sizes, we can actually still, it kind of looks like a hill shade or a slope shade in the landscape. And we can also see some artifacts from that pixel differences. But there are some real changes in there too. So again, reason it kind of shows you where the channels are, the edge of features are, because of the difference in pixels. If you were to like try to graph their differences out in a profile graph, you'd see that on one side of the slope there would be kind of averaging above a different resolution data set, and later in the slope it would be averaging below. And so then we can see those changes in the difference map. Okay, so yeah, so we can see that it goes from 27 meters higher to 23 meters lower. 27 meters higher, well, I don't know what that is. Maybe some structure was put in, or possibly there's really tall trees up in the hills. I don't know. But there's probably not a lot of data that's different. The 23 meters lower could be where we're excavating new gravel pits. But you know, it's not, you can't get a lot out of this kind of symbology here, and it's better to go into the real symbology and again look at classifying and the histogram there. And so we want to click on the histogram. You can see there's actually very little that's way up there or way down here. Most of the change is within plus or minus 7 or 10 meters or so. And so if we really wanted to kind of classify this well, we could say, okay, let's look at this extreme stuff out here. Let's look at kind of stuff that's maybe more common here and more common here. And again, the extreme stuff out here. So stuff that's not very different is kind of here. I don't like this color scheme, so let's change that. Could have a stark contrast where it goes from reds to greens. So yellow is not much change, plus or minus 5 meters. Green is significantly lower, so gravel mining excavations. And then red is significant, and orange is significantly higher. I did manual interval. You could do some sort of equal interval or quantile as well, and that, you know, that is probably a little bit more quantitative, but it might not highlight the very specific features you might want to be looking at. We could do equal interval. Takes a minute to reload. So this equal number of pixels between each value change is what that means. And yeah, we can define them ourselves, or we can make a kind of scrolled manual interval, which I just did. A geometrical interval. Let's see how that looks. Or you could just make it nice round numbers. You could tune it down so like maybe we've got more classes, like 8 classes, right? And then go to manual interval or defined interval, and we could say the interval size is 5. So 0, 5, etc. Okay, well, this is nice because we can say keep it around 0. So maybe let's go every 2 meters. We'll get a bunch of classes. And now we can see, okay, where is it that we have gravel mining? Where is it that maybe we have some slope changes on the hills? Possibly due to vegetation represented or not. Yeah, that's pretty good. We'll stop there. Okay, so yeah, hopefully you saw in this video how to first basically we were able to clip the rasters, and then we were able to in detail interrogate the differences between the rasters using their statistics. And also we're able to use raster calculators to subtract one from another to potentially look for landscape change like that due to gravel mining over time here at the Stockton Bar. And we can see that gravel mining if we zoom in. And if you want, we can always go to appearance and make this a little transparent so that we can see where, if that mining is lining up with what we see here. Of course, what we're seeing here is LiDAR, which is even more recent, so we may have new mining going on. And also it's a different resolution, but we can see it sits where it should. And then also where those differences are in the slopes. Higher tends to be where the trees are, lower tends to be where the trees are less. So that makes some sense as well. All right, hope this video helps. Happy mapping.